right, so the lecture is getting recorded. You do have one homework starting today, and it has to do with relations. So right here is a relations homework. It's in the form of a quiz again, okay? But you have an entire week to work on it. So it's due next Monday at noon. So you have 1 week to work on this one. Yep.
I want to let you know that our data structure class has an exam
Next Wednesday. So you want, okay, that can be a little bit of a problem. Okay, so if I were to make the exam for this class on next Monday, we're going to have to go through the practice exam today. But the homework is also due on the same day, which is not going to help you study. That's the problem. So if that is the case, yep.
Is Monday a holiday?
It's off.
There's no Monday.
Oh, it's Friday,
okay.
Monday off.
Yeah.
So we're going to have to do it on Monday after then. Okay, all right. That works for me. All right, so let me see. Where's the calendar? There should be a calendar somewhere.
Yeah, no, I check the link today.
You just Google ARC academic calendar.
No, I'm trying to make a calendar for this class, so just so that people don't forget that we're gonna have an exam like 2 weeks from today, basically. All right, so first exam on. So today is the 12th, so 2 weeks would be 26. Okay, all right. The nice thing about that is I can include more material into the first exam now. Okay, so first exam on the 26th during lecture time. There we go. Okay. All right, so it is now scheduled. I'm going to go over the practice exam on Wednesday, not today. Okay, so we'll go over the practice exam on Wednesday, but we're not going to have the exam on Wednesday because data structure has its own exam on next Wednesday. So I will try to kind of stagger the exam so that you guys don't have to take 2 exams on the same day. Sometimes it actually works better because certain classes are related. So when you study for one class, your mind is actually ready for the other class as well.
So just like with calculus and physics.
Calculus, well, it depends on which calculus and which physics.
That's true.
But yes, but if you're studying Newtonian physics and you're having calculus exam on the same day, sometimes it helps out, because the topics actually are related. Yep.
Is there going to be like a sample exam for?
Yes, on Wednesday we're going to go over a sample exam.
Are you going to post something on campus?
Maybe, because the order of topics is changed from last semester. So when I use the exam of last semester, it does not match what we are going to have for this year, for this semester. So, but yes, I will post something before Wednesday, but even if I post on Wednesday, you have more than a week to work on it because it's like 2 weeks from today.
Yeah, I was just seeing the exam 2 samples are on there on campus already.
Ah, okay. Yeah, I can just copy something in a shared folder. All right, so that is out of the way. So we can now go back to the Aleph null concept. And last time we were just talking about the how to come up with a closed form for the summation. Do you guys remember? That was kind of what we were working on. Okay, so let me just scroll down to where we are at this point. Sorry.
Just wondering why your voice became quieter.
Oh, I cranked it down, but it's like too little now. If I crank it up just a little bit, is that good?
I think it's good.
That's good. Okay.
I love your voice, Mr. Tack.
Well, I don't like to listen to my own voice.
But we like it though.
Who does?
I get to listen to it all day long already, just inside my head. I don't need to go through the outside, listen to it, from the outside.
Infinitely.
Yep. All right. So last time, we were basically looking at this. If we just kind of stay with a y coordinate of 0 and just use x as a variable, we end up with something that's relatively simple. We just end up with, it's just a summation of 0 all the way up to x. That was the discussion last week. We got to that point. So now the question is, but is there a closed form for this? And I distinctly remember last Wednesday, I said, well, if the number of terms is even, then it's really nice because the first item pairs up with the last one, the second item pairs up with the second last item, and they all add up to x itself. So it's pretty easy to figure out what the sum is. On the other hand, if it's an odd number, then we pair the first with the last, second with the second last, and then we have one single item left over, which is half the value of x that doesn't pair with anyone. Okay, so that's why we end up with this equation here. Okay, so g of x0 is 0 plus 1 all the way up to x. Okay, that's something that we talked about already. And we just say, we can use a sigma notation to denote that. So are we all familiar with the sigma notation at this point? The summation? Yes?
Yes.
Yeah. Okay. Yep.
Can you scroll up a little bit? A little bit more. Okay,
Okay. Well, we, even if you didn't read the notes, we actually talked about this last week.
No, I
Yeah.
did read the notes. It's just something I forgot to write down.
Oh, okay.
Yeah.
Okay. All right. So just like with the, I'm not sure whether it was with this class or not, but that's okay. So we are using a ternary expression here to basically say if x is odd, we go with this one. If x is even, then we go with the other one. Is that okay? So when you look at this expression, it is either true or false. Okay, it's either true that x mod 2 does not equal to 0, which means x is an odd number, or x mod 2 is 0, which makes this comparison false. Okay, so by using the ternary expression, which is which involves a question mark here and a colon down here, we can say this is the then expression. This is what we evaluate when x is odd, and this is the else expression, which is what we evaluate when x is even. It is counterintuitive because when x is odd, the number of terms is even because we start counting from 0. Is that okay? So when x is 5, we have 0 plus 1 plus 2 plus 3 plus 4 plus 5. So we actually have 6 terms in the summation. When x is odd, when x is even, we actually have an odd number of terms, and that's why we have a little x divided by 2 that is outside of the sigma notation. It's just kind of freestanding on its own and not really related to the sigma notation. Is that okay? So I break it up into these two because intuitively we kind of have to treat it differently, whether it's odd or even. So how do we go from the first line to the second line? Let's assume that the first line makes sense. How do we get from the first line to the second line? Well, actually, let me take one step back, okay? Let's get to how did we get this first line in the first place? Because initially, all we have is just a single sigma notation. How did I break up this one single sigma notation into two sigma notation? If you look at the range of the value of the index, what did I do to kind of make something simple look more complicated? I just break up into 2 halves. Okay, so in the case when x is odd, I break it up into 2 halves. So the first sigma only takes care of the first half of the sigma of the series. I goes from 0 to x minus 1 divided by 2. Okay, x is odd, x minus 1 is even. An even number divided by 2 is a whole number, it's an integer. So that should not be a problem. And then the other sigma starts with 1 more than the end index of the first sigma to continue the series, all the way up to x itself. So is that making any sense? You know how I just broke it up into two halves? Okay. And I did something just like this with the even number, except in the case of an even number, okay, let me scroll here, except in the case of an even number, x divided by 2 itself is already a whole number, it's already an integer. So I subtract 1 from the x divided by 2 with the first sigma, and then with the next sigma, I start with x divided by 2 plus 1. That would actually be wrong, wouldn't it?
Because you separated out the x over
Oh,
2.
right, because the x divided by 2 itself is out, out here. Thank you. I forgot about that. Is that okay? All right. So now how do we go from this line to this line here? What did I do? How did I combine it? I adjusted the expression so that I can use the same index as the first one. Is that making any sense? So if you look at the first item of the second sigma, this is just I, which is going to have the value of x divided by x minus 1, the whole thing divided by 2 plus 1. Okay. But when you look at the combined version, you know, it's going to be x minus 1. And then that I goes x minus I, but I is 0. So when you look at the first term here and the first term here, I think it's the last term here, they are the same. When I is x minus 1, the whole thing divided by 2, x minus I, the term itself, is going to be the same thing as x minus 1, the whole thing divided by 2 plus 1. Is that working out or not? Okay. This is all in sigma notation. Okay. And with this one, I did exactly the same trick. Okay. I combined the two sigmas by adjusting the term in the sigma so I can reuse the index. So I can just add one more term to the first sigma notation to accommodate both sigmas. Is that okay? But the term that is left over, the x divided by 2, is still sitting out here, outside, because it is not a part of the sigma notation. So are we okay from here to here? Okay. What about from here to here? What did I do? You can see the I term is still the same, but the term that we are doing a sigma over, hey, that looks familiar. It's just x all by itself. Why?
Cancels
out. The I cancels out. Okay? So that's why I'm just summing over x itself. What about on this side? I didn't do a single thing on this side, so that's kind of left alone. Okay, so how do we go from here to here? How did I lose sigma altogether?
There's no I.
Because the term that we are summing has no dependency on I. It is x. X has no dependency on I. So when I have this term here, it means I'm just adding x so many times. Okay, so instead of using sigma, we know something that works better, multiplication, right? And that's why I'm multiplying x by whatever the n index is plus 1, because we start from 0. Is that making any sense? Okay. What about the other side? On the other side, basically the same kind of trick, because I and negative I or minus I cancels out. So we are just adding x. But this time it is x divided by 2 minus 1 plus 1 times, and then the minus 1 plus 1 cancels out. So we just have x divided by 2 times x. Okay, and then the other term, the x divided by 2, is separated and it's never really considered as when we work with all that sigma stuff. Is that okay? Mm-hmm. Okay. So how do we go from here to here? Yep. So you basically say, okay, let's use the same denominator. So the plus 1, which have no denominator, is now 2 divided by 2, and I just put it up here. Okay. And what about on this side?
Get rid of the parentheses.
Yep. I just got rid of the parentheses, Yeah, that was the only thing I did, was to get rid of the parentheses, which was not needed. All right, from here to here. Simplification, the x gets on here, and then x minus 1 plus 2 is just x plus 1, so the x plus 1 goes here. On this side, what did I do? Factoring, okay? So I factor out x divided by 2, so this guy is basically x divided by 2 times 1. The other one is x divided by 2 times x, so we have x plus 1.
We now to have seen an exclusive. California is investigating insurance junk.
Are we recording, by the way?
It is being recorded as well. I think in the class and kind of kind of say ask Siri, ask Google, and so on and so forth, and just to ask you, just to have your phones to respond. Okay, so but are you convinced that this term is the same as that term?
Yeah.
They are the same, indeed. So if I simplify, or just present it in a nicer way, I'll just have both sides to look like this, x times x plus 1, the whole thing divided by 2. And then you look at these two and go like, hey, they are exactly the same, they're identical. Which means the ternary operator was not needed in the first place, because regardless of whether x is odd or even, I end up with the same expression. So that's why, when you look at the last line is really cool, because we just say, hey, we don't need that ternary operator after all. Whether x is even or not, we end up with x times x plus 1, the whole thing divided by 2. So are we good with this so far? Okay. So the derivation is not something that you have to memorize. Okay, there's nothing you really should be memorizing in this class, because your exam 2 weeks from today is going to be open book and open notes. Okay, anything that's either handwritten or printed prior to the exam, you can bring. So that means you can print out my own notes if you feel that is useful. You can bring your own notes too, because many of you are taking notes during class. You can bring that too. Or if you want to study with 3 other people, and you guys want to say, okay, let's share notes and come up with a compiled, bigger and more complete version of the notes, you can each bring a copy of that with you. You can go to the library, okay, and check out books on discrete, structure. And you go like, okay, I found these 20 books that are all useful to me. You can have a little hand truck, okay? You'll be sitting on that table right over there, okay? You'll be the x divided by 2, kind of all the way over there, okay? So that is the format of the exam, okay? It's open book, open notes, literally, but no electronic tools other than a scientific calculator. Yep.
Do you expect us to do a derivation just like this with a different?
No. The derivation here is really more for myself to convince me that it makes sense. Okay. Now I know many of you already know. Okay, with that sigma notation, you learned in other classes that it simplifies to x times x plus 1, the whole thing divided by 2. And the proof of this can be done in a variety of ways, including, but not limited to, proof by induction. Okay, so if you want to prove the sigma of I goes from 0 to x, and then I really equals to x times x plus 1 divided by 2, you can prove that by induction. But the derivation shows, basically say, okay, we can see how it expands, but how do we come up with a closed form? Not saying that, oh, now we have a closed form, prove that it really is the same thing as the sigma. Because those are 2 different processes. One, you start with an answer, you start with a solution, and then you just want to validate and say this answer does work. The other one is saying, okay, you start with something that is kind of ugly, and you're trying to come up with an elegant way to express the same thing. But the short answer is no, I'm not expecting you to make derivations like that. However, the tricks that I use in the derivation like that, you should understand. Okay, like all the things that I do with the sigma, how we change the indexing or how we change the term itself, to kind of shift things around, that you should understand. Is that okay? Are there any questions about what is in the exam or what is not in the exam? Okay. All right. Okay, so according to this note here, now that we know how to get G computed for all the pixels at the base of the diagonal lines, how do we compute the G value of the other pixels? So let me see if I can dig up that picture that we had already done in the past. We still got it. And let me open it up. It's interesting. Visor is a Chrome extension, which means it's operating system independent.
Oh wait, visors?
Visor,
Yeah.
the tool that I use for screencasting my tablet,
Yes.
is a Chrome extension,
Okay.
a browser extension. So it's a pretty handy one. There we go. So we got this picture again. So now we know how to compute the 0, 1, 3, 6, 10, 15, and so on. So now the question is, what about the other pixels, on the screen? Well, but we know how we filled up the diagonal lines, right? In other words, if I point to a particular pixel, okay, the first thing I need to know is which diagonal line are we talking about? And that we have a few ways to count. So intuitively, we can just count like this. This is the first diagonal line, which is just a single pixel by itself. This is the second diagonal line. This is the third. This is the fourth, and so on. And once we know which diagonal line it belongs to, we know the base of that diagonal line. The y coordinate is simply adding to the value itself. This is this is the base of the diagonal line, which starts with the value of 10. When y equals to 1, it has a value of 11. When y equals 2, it has a value of 12. So the y value is just being added to the base value of that diagonal line. Is that making any sense? So we can, in fact, get to the value of every single pixel. So now the other question is, how do we know which diagonal line we are talking about? What do you think? You're given the xy coordinate. So how do you know which diagonal line we need to look at first? This is diagonal line 0, diagonal line 1, 2, 3, 4, 5, 6, and so on. So when you look at the pixels, what do you notice? Everything on the same diagonal line shares a particular thing. What do you think that thing is going to be? X plus y is the same. Okay, let me see if I can illustrate here. And this time I'm going to pick the color red. There we go. Okay, so this is coordinate 0, 0 right here. Okay, and of course that's not really telling you much because 0 plus 0 is 0. So it's telling you that we need to look at diagonal line 0, which is just a single pixel. Okay, so it's not really that helpful. So we look at the next diagonal line. This is 1, 0, and this one is 0, 1, right? But they belong to the same diagonal. 1 plus 0 is the same as 0 plus 1 because they both belong to diagonal line 1. Okay, and the base of that, which is this one here, has a value of 1 times 1 plus 1, the whole thing divided by 2. Is that okay? So that this is relating back to what we learned about the G value, the simplified G value earlier in today's class. So we now move on to this one. This is 2, 0. This is 1, 1. And this is 0, 2 as a two-dimensional coordinate. Once again, you can see that 2 plus 0, 1 plus 1, and 0 plus 2, they all add up to 2. But what about the value at the base? It's 2 times 2 plus 1, the whole thing divided by 2. So we are dealing with 2 times 3 divided by 2, which turns out to be 3. Let's do one more diagonal line, just so that we feel comfortable with it. This one is 3, 0 as a coordinate. This is 2, 1. This is 1, 2, and this is 0, 3. Do you see how when you add up the x and the y of the coordinate, they all add up to 3 this time? The value at the base, okay, the value at the base here has a value of 3 times 3 plus 1, which is 4, the whole thing divided by 2. So we're dealing with 12 divided by 2, which turns out to be 6. So it all kind of works out. Is that okay? So that's why, you can use, okay? So basically x plus y IDs the diagonal line. Diagonal line. Is that making any sense? So give me any x, y, give me any coordinate. I just have to add the x and the y coordinates, and I know which diagonal line it belongs to. Okay? So we'll just call it D for diagonal, okay? And then D times D plus 1, the whole thing divided by 2, is the value at the base of that diagonal line. Yep.
What about away from the base?
Away from the base? Okay. So now we basically say y plus d plus 1, the whole thing divided by 2, is the value at xy. Is that okay? So that's kind of cool, because now we actually have a function now, right? So now if I rewrite this a little bit, just kind of make it look nicer, we can now do this. I'm just gonna reuse what I have here, get rid of the question mark, because now we actually do know what it looks like. So now we can look at this and say, yep, we know what it looks like now. It is x plus y, which is d, times x plus y plus 1, which is d plus 1, the whole thing divided by 2 plus y. That is g of the pixel xy. Is that okay so far? All right. That is kind of cool, because now we actually do have a function to map from the two-dimensional space spanned by natural numbers, as the two axes, and we can map it to just natural numbers. Okay, so every time we have a function, then we have to ask a few questions. Well, first of all, is this a function? Do you guys do remember what makes a function a function? What makes a function a function?
It's a meter that has both coordinates, the x and the y, but it cannot have them repeated in some way.
For every possible, for every element in the domain, it has to map to one and only one element in the codomain. Okay, so the only way, there are two ways for a mapping or a subset of the Cartesian product not to be a function, right? Okay, the two ways to make it not a function is, I can find something in the quote-unquote domain where it does not map to anything in the codomain. Okay, do we have that situation here? Can I point to a particular pixel somewhere and say, it does not correspond to a natural number? We cannot, because the equation here applies to any possible value of x and any possible value of y, as long as they are natural numbers. Okay? If that is not the case, what about the other way of a mapping or a Cartesian product not being or a subset of a Cartesian product not being a function? One element of the domain, the quote-unquote domain, maps to two things in the codomain. Okay? How do we make sure that does not happen? Well, we look at each function here. Is addition a function? Is addition a function? Is division a function? Is another addition a function? Well, this is a composite of only functions. You end up with a function. The composite of functions has to be a function. Okay? So now we know G is a function. So knowing that G is a function, then we can start to ask the questions. Is it injective? And is it surjective? It doesn't even make sense to ask those questions until we know that G as a subset of the Cartesian product is a function. But now that we know it is a function, is it injective and is it surjective? How would you answer those questions? Not from the sense of a proof, just intuitively. How would you approach and answer those questions? What about injectiveness? What does that mean? If a function is injective, then what do we know about that function?
Only one output encoding, or maps on one element encoding.
Go ahead. Uniqueness. Okay? If two different elements in the domain are guaranteed to two different values in the codomain. Is that okay? Can we prove that is the case now that we know that this is the function? Okay? It's just, but you can also use algebra. So you can use algebra and basically say, if you do not have the same, if x, okay, so you pick two pixels, x1, y1, and x2, y2. And then you can use several steps, okay? It's not going to be one simple, nice, and clean proof, but you can show that if x1, y1 is not the same pixel as x2, y2, then the G value is guaranteed to be different. You probably will have to break it up into three different cases. One case where x1 and x2 are the same, but the y's are different. One case where y1, y2 are the same, but x1, x2 are different. And then one more case where x1, y1 are both different from x2, y2. So you probably have three separate cases. But it boils down to algebra. Okay? So you can use algebra to show that, yep, G is injective. What about surjectiveness? What does that mean? Everything in the codomain is mapped to. Okay, very good. Okay, so can we intuitively think about it and say, yep, it makes sense? Okay? Because, if you look at the entire space, you can pick out, any pixel and go like, is it mapped? Yep. Or, oh, excuse me, I take you back. You have to look at natural numbers. Okay, you have to look at the codomain, so you have to look at natural numbers. And you ask the question, the reverse question, and say, is a pixel mapping to this natural number? How do you solve that problem? I mean, intuitively, how do you know that it is surjective? So I say, okay, here's 4096. Okay, is it mapped to? How would you say that? Yep, it is mapped to.
Just as a combination of functions on codomain.
But how do you know that this function will give you a value of 4096? There's a pixel xy to give you that particular value. How do you know that?
This is just addition.
Huh?
It's just addition on the right side, if you look at it.
No, but that does not guarantee it.
Can you do the inverse?
Hmm?
The inverse?
The inverse is kind of tricky because when you think about the inverse, you already know that it is surjective. So you kind of have to answer the question of, is it surjective first? Yep. Yep.
But isn't that a possible way to prove it? Because if we already know it's injective, and because of its injective and surjectiveness is bijective, couldn't we assume it was surjective?
No, but we don't know it is surjective. That's what we're trying to answer right now is it surjective?
Well, wait till we get the other information.
Okay, go ahead.
I guess intuitively, like it goes like diagonally through all the x values, so it's not like it's gonna have like a hole in it at some random point.
Right, so if I give you a very specific example, like 4096, you can actually do it like.
If I really wanted to, I could show you that, yeah.
So you can spend like maybe half an hour and figure out, okay, C tag,
Like,
this pixel, gives us 4096.
I think it's
Do we
Yep.
already know that the codomain
Mhm.
contains all natural numbers, or do we not know that? We can't say that.
Say that one more time.
Do we already know that the codomain is a set of all natural numbers?
Yes, we do.
Okay.
But how do you know all natural numbers are mapped to from pixels? That is the question. It's a little bit tricky. Yep.
I was thinking whether or not set G equal to 4096, and then see if you can get two separate values of x and y, like a version of 4096 is divided by or multiplied by version of x equals to some y.
But the problem with that approach is we only know in that case that 4096 is mapped to. What about 4097? Any ideas?
I think we give up.
Okay, so I haven't really done this before. Let's try proof by contradiction. Okay, which is basically saying, let's say G is not surjective. Something is not mapped. Okay, so a particular integer, a natural number n is not mapped from anything from the domain. Is that okay? So then you go like, okay, so if n is not supposed to be mapped, then I should not be able to find a pixel, xy, that maps to n. Is that okay? So let's go ahead and see what that would look like. I've not done this before, so this is the first time that I'm doing it. Okay, so we'll say prove by contradiction. So in any proof by contradiction, you have to negate the theorem first. So we have to say, oh, what is it that we're trying to prove? Are we proving that G is a function? No, we have done that already. Are we proving that G is injective? Nope, we have done that also. What is the focus right now? G is surjective. Okay, that's what we're trying to prove. Okay, so when you prove by contradiction, the first thing you have to do is to negate the theorem. You negate the very claim that you're trying to prove. You have to say, let's say that is not true. Okay? Okay, so our theorem is basically saying G is surjective. That's what we're trying to prove. So the negated theorem, guess what? Is saying what?
Not certain.
G is not surjective. Okay. So the negated theorem is saying G is not surjective, which implies what? Okay, G being not injective implies there exists xy, okay, as a coordinate in n Cartesian product with n, because that's our domain, right? So I'm just picking an element out of my domain, and basically we say xy. Oops, I take it back. Okay, you're gonna hate this, but you can also do the same thing because I flipped the domain again. Okay, so I should say there's an n in just natural numbers. Okay, where there does not exist, okay, that you can look at this at there does not exist xy in n times n such that G of xy equals to n. Is that okay? This is the result of claiming that G is not surjective. If G is not surjective, then at least one element of the codomain, which is our natural numbers, is not mapped from anything from the domain. Is that okay? Okay, all right. So then we can say, but this also is implying, or is actually equivalent to, there exists one n in natural numbers, such that for all xy in natural number Cartesian product with natural number, G xy does not equal to n. Is that making any sense? I'm just flipping the, I'm distributing the negation to the inside right here and changing the quantifier from a not exist to for all. Is that okay? Okay. All right. So now we can think about an inverse function, okay? Because we're trying to figure out, hey, if you give me n, I have a systematic way to go back and figure out what coordinate x, y will go through G and give me this value n. Is that okay? Okay, so now, what we need to do, need to do the following, Given n as any natural number, can we figure out some kind of x of n, some kind of y of n, so that this particular pixel, the g of this pixel, is actually n. In other words, we're trying to figure out the function x and the function y, so that you can give me any natural number n, and I can give you the x and the y coordinate of a pixel, so that the g value of that pixel is n. That becomes our question. So indeed, we are looking for an inverse function. Because if an inverse function exists, then we can show that g is surjective. Is that making any sense? Okay? All right. So now we have to look at this problem a little bit differently, From the perspective of the original problem, now we are looking at this situation, Now we have a two-dimensional space, and I'm just saying, here's the number, 6,000, Where is the pixel corresponding to 6,000? That is now the question. Is that okay? In other words, what I'm looking for is, how do we figure out that? How do we figure out the x and the y such that when you apply x, y to this whole thing, it is actually 6,000? Yep.
So this is the equation we're going to be using to solve all the problems here, or will that equation vary? Like, in other words, I was just saying that this is the equation we're going to be using to
No,
solve.
this is just an example, but from working out a single example, we hope that we can generalize it so that we can actually derive the equation needed for just give me, so right now we're just solving for one single natural number. Somebody's gonna say, oh, well, we kind of know how this works. We just have to hire a whole bunch of interns to actually fill up the table until we get to 6,000. Then we can figure out what is x and y, right? But once again, that only shows that 6,000 is mapped to. What about 6,001? Oh, but that's just the next one. What about 16,000 then? More interns, right? Yep.
The equation that we derived earlier, can we substitute in, we have y equals something with the d?
Can we substitute?
The diagonal equations you had earlier?
Well, the nature of the problem is this. So how do we figure out what is x and y? The first thing we need to do is to figure out the diagonal line. So which diagonal line will give us something close to 6,000? Because once we figure out the diagonal line, the y is easy to figure out. Just 6,000 minus the base value of the diagonal line. We're done. So the key really is, how do we know which diagonal line is going to do this?
Set it equal to it? You set it equal to it?
Set it equal to it? Okay.
So the equation.
All right, so let's check out this. So how about we turn it into inequality? Okay, so how do we turn something like this into inequality? So so at this point, I'm generalizing the whole thing back into n. Because because this approach works for any integer. So can I claim this? How about this? I define d to be x plus y first, because I don't like to write x plus y all over the place. Is that okay? Just by definition, d is x plus y. Well, we don't know what x is, we don't know y is, but that's okay, because we are just saying, instead of looking at x and y individually, we'll just say d is x plus y. Yep.
Well, So, I think you'll get it.
Yeah, if you have read the notes, this is going to be extra boring because I'm just repeating what I have already written in the notes. Okay. But that's assuming you understand what I'm writing when you read the notes. I have been told that I have ways to write about something in an obscure way, so it's actually difficult to understand. It's a byproduct of writing a dissertation for PhD. No, I'm just kidding.
Oh, okay. I took you serious.
Okay, so let's check this out. Okay, so we'll go ahead and say, can we turn this into an inequality? In other words, the first thing we can do easily is to say, okay, we have d plus 1, the whole thing divided by 2, plus y equals to n. Right? By definition. That just has to do with how d is defined. Are we good at that? But now we have many unknown terms, right? Because y is unknown, d is unknown, d depends on x and y. But we have two unknowns, basically. We have two unknowns and only one term that is known and only one equation. It doesn't work. Okay. So my job is to now say, let's get rid of some unknowns. But when we get rid of one unknown, we're turning the equation into an inequality. So the question now is, what do I do with this equality here so that I can use another relation down here? What do you think? Can I? Yep, go ahead.
Say less than or equal to.
Yep. But how do we know that for sure?
Because y can be a real number.
Because y is
A positive integer.
a natural number. It cannot be negative, okay? Because if y can be negative, I cannot establish this. But since y cannot be negative, it can be from 0 and up. I can just say, hey, we can lose this term, but then we change the equality to an inequality, like that. Is that good? Is that okay? All right. Okay, so I'm going to copy and paste a few things to the next slide. So we'll just go ahead and copy this, open the new slide, and paste it here. There we go. Well, let's go ahead and multiply things out a little bit. So we'll end up with d squared, oops, change the tool, d squared divided by 2 plus d divided by 2, and we'll say that's let's see, d minus 1, no, that's just half, right? Minus n is less than or equal to 0. I mean, does it work for you? I just multiply out the terms over here and then subtract n from both sides, so the other side is a 0 and one side has a minus n. Is that okay? And d is unknown. N is already given. We know what n is. If you just kind of ignore for now what this is, what does that look like?
Some factor.
Quadratic, right? Okay. And if I just for now say, we're just going to pretend that this is equal. Do we know how to solve this if it is actually equal to? Yeah, we know is it negative 3 plus minus square root of something, right? Okay. Okay, so you guys get to tell me how we solve for d. Okay, so if we were to actually say this is equality, how do we solve for d? So minus b, right? So b is 1/2. Okay. Plus or minus the square root of 4ac minus b squared, right? So b squared minus 4ac. Okay. So b squared minus 4 times 1 times negative 1. This n, that's n. Huh? Times 1/2. B squared minus 4a. Oh, okay. That's a. Okay, so This is A, this is C, and then the whole thing divided by negative 2A. I think it's just 2A.
Yeah, it's just
Yeah.
to
Yeah. So 2 times A is 2 times 1/2, which is just 1. Okay. Okay. Details. But what is not detailed is, well, we got two numbers now. Okay? And whatever this is resolved to is not even a natural number. What are we going to do with that?
We can infer that the radical only contain positive numbers.
Okay? So D cannot be equaling to this because D is x plus y, right? So how do we turn a potentially irrational number back to a natural number? We got 3 ways to do it, right? We can round, which means if the fractional part is at least 0.5, we round it up. If it is less than 0.5, we round it down. We can do a floor, which means we take whatever is the largest integer that is still less than or equal to whatever this number is, or we can take a ceiling, which is the other way around, the smallest integer or the smallest integer that is less than or equal to whatever the thing is inside the ceiling. So which way do we want to do it? And the other problem is we got 2 roots too, right? And because we know D is x plus y, which root cannot be the one that we're looking for?
Negative 1.
The one that is the negative. Exactly. Okay, so now we know that we can erase this, get rid of that. Whoops. Right? Because we know that we don't care about the solution where, when D goes negative. D cannot be negative because x is a natural number, y is a natural number. The sum of 2 natural numbers has to be a natural number itself, so we know we can get rid of that minus. Okay. What else are we going to do? Well, we need to turn the rational number into a irrational number into a natural number. So the question now is, do we take the floor of this? Do we take the ceiling of this? Or are we just going to round it? That becomes the next question. To answer that question, we have to look at the original inequality here.
So we take the ceiling.
We're trying to figure out the largest D so that this term is still less than or equal to 0. Okay? So we're looking for the largest D so that still happens, right? So should we floor or should we take the ceiling? We should take the floor. Okay. So we just take the floor of this whole thing. That would give us D. Alright? You guys are looking at this math and go like, I'm not really sure about this. Right? So we'll plug in some numbers. Okay, we'll figure this out. Okay, but before we do that, we'll clean it up a little bit. Okay, so this is the floor of negative 1/2 plus the square root. Huh?
You can get out the 1/2 of the square root. Just multiply the second side by 2. So it'd be 8 times 1/2 times negative 8. If you get out the 1/2.
But doesn't it boil down to this? I'm just combining these terms over here. So 4 times, oh, okay, I guess it's 2n, right? Okay. Okay. Because 4 times 1/2 is 2, and then the negation cancels out, so it becomes 1/4 plus 2n inside the square root, and then we still have this negative 1/2 outside of the square root. Yep.
How do we know that ceiling won't work over floor?
Well, the ceiling is not going to work because if you take the ceiling, then we are looking at a natural number that is going to turn this into a greater than or equal to. Because the ceiling of a particular value is greater than or equal to whatever the value is supposed to be to begin with. Is that okay? And the d, without the floor function, this d is actually will make the quadratic equation equal to 0.
Okay.
So when you take the ceiling, then you're taking a larger value so that it would actually exceed 0.
Okay.
So that's why we take the floor. Okay. All right. So we'll test this. How do we test this? In other words, how do we, given a natural number, can we figure out which diagonal line correctly? You still got that picture, right? Remember the picture that we looked at earlier? Okay, so we're going to use that to help us. And we'll test the extreme cases first, okay, the boundary cases, like when n equals to 0. So what happens when n equals to 0? Okay, let me clean this up a little bit so it's actually easier to read. So get rid of this mess down here, clean it up. Okay, that looks good. Okay, so when n equals to 0, what is this? Okay, 2n is 0, then we have a quarter, but we're taking the square root of a quarter, which is half, right? We have a negative of half of the outside, and then we add a half to it, we got 0. So is 0, 0, which has the value of 0, is it on the diagonal line labeled 0? Yep. Okay. Let's pick something else. Let me go back to the earlier page. Yeah, we can pick. Okay, which one do you want to pick? And want to try 12? Okay. So before we go back to the other page, 12 belongs to which diagonal line? So 12 belongs to diagonal line 4. Everything, if you add up the xy on that diagonal line, all the xy would add up to 4. Is that okay? So if we plug in n equals to 12, d should be 4. Is that making any sense? Okay. So now we scroll all the way back to the last page here. And then we say, okay, so n is 12. Okay? 212 is 24. So we have 24 and a quarter. What is the square root of 24, just approximately?
It's a little bit less than 5.
Just a little bit less than 5. Very good. Okay. So it's a little bit less than 5, but more so than half, probably. Right? So we end up with 4. Does that make any sense? Because it's 4 point something on this side, and then we minus 0.5 from it. And the answer is 4. So d equals to 4 when n equals to 24, when equals to what? 12, and it does work out. So now we have a closed form to find d. Okay? So now, instead of just saying that this is d, okay, we'll just kind of make it a function. So d of n is this mess here. Because the value depends on n. Is that okay? Alright, if we can figure out the d, can we figure out the x and the y? Because d is supposed to be x plus y, right?
Yep.
How do we figure out those two? Let's deal with y first. Okay, if we know what n is, and we know what d is already, how do we figure out the n? Okay, so we know somehow this has to do with, there's an n here, there's a d of n here, but how do we figure this out? N is given to you. Yep, go ahead.
Yeah, you can go back to the kind of the original equation, but for x plus y stuff, you need to solve for y.
It'll be that, right? It'll be n minus d of n. Because n is the number itself. Oh, you're right. Okay, that's not just d of n here. Okay, take this. Get rid of this. This is now negative g dn as the x coordinate, 0. Okay.
Black screen. I want us to write down the black screen too.
Okay. Is that making any sense?
Not yet.
Not yet? Okay, so let's go back one step at a time. Let's focus on just this part here. Okay, what is that going to give us? Okay, first of all, what is D? What is D representing?
X and Y.
D is
plus Y.
the diagonal line, which is also known as the x coordinate at the base of that diagonal line, right? Okay, if that is dn, what is the coordinate dn comma 0? That's at the base of the diagonal line that we're interested in. Okay, it's the coordinate of the base of the diagonal line that we're interested in. Is that okay? But that's a pixel. It's a coordinate. So if it is a coordinate, can I apply g to it to figure out the value, the natural number of that particular coordinate? Yes, we can, right? Okay. So I'm negating it, arithmetic negation on the outside, and basically I'm saying, okay, n minus the g value of the base. What is that going to give us? N is the value of the pixel that we are interested in, right? So what do you get when you have n minus the value at the base of the diagonal line? You get a y coordinate. Okay, so if we can figure out what is y of n, how do we know? How do we figure out n x of n? The x coordinate corresponding to that. Okay, how does x and y relate to d? Exactly, d is x plus y. And do we know d of n? Have we defined d of n? Have we defined y of n? How do we define x of n? Subtraction, exactly. So this is d of n minus y of n. Is that okay? It's convoluted a little bit, okay, yes. But yes, but we can get to it. Is that making any sense? So, what does the actual function look like as a reverse function? As an inverse function? Okay, well that's why I have all of this stuff typed up. So the reverse or the inverse of g is this. So this is g inverse of n. It is kind of ugly because I have a w thing to deal with just the square root thing. Okay, so it's the same thing except it's presented differently. Okay. But that's w of n, which is the same thing as what we did earlier, which I called d of n earlier. So we have this thing here, which turns out to be just the g applied to that thing, minus n, and then n minus that whole thing. This becomes the inverse function. You give me a single natural number, n, I'll give you the pixel corresponding to that natural number. I can reverse the whole process. Yep.
Where does the plus 3 come from?
The plus 3, because this is x, and so it has the plus 3 comes from, okay, so it comes from this equation here. So we have an n that is, we have a wn on the outside. So when you want to have a single denominator, this becomes 2 divided by 2 times w of n, and then you can combine it here. So that's why we have a plus 2 in the parentheses. So 1 plus 2 is the 3, and that's why we end up with a 3 here. Is that okay? Sure. Okay, so the pine needles is definitely a little bit messy, okay? What about the pine tree? I mean, after all this math stuff, okay, what are we showing? There's an inverse function, which proves that the G itself is surjective. So it's injective, it's surjective, it is bijective. And well, it's kind of clear because we worked out the inverse function to show that. Okay. So now that we have the pine tree, what is the pine forest? I'm surprised nobody has asked, so where's my pine sol? Okay, so where's the pine forest? What is this what is this, why is this useful? Other than, oh yeah, we have this whole discussion of coordinates versus natural numbers and they can map to each other. Okay, there are two things that is really significant out of this entire discussion. Okay? What? Yeah.
Is it that each pixel can be stored in just one value?
That is cool, isn't it? Okay? But there's one more thing. Which module are we on? Aleph null. Okay, and Aleph null basically it says what? What is Aleph null by definition? Is the cardinality of natural numbers. Okay, so the cardinality of pixels in a two-dimensional space where each pixel is a natural number, comma, a natural number, it has the same cardinality as just natural numbers. That is kind of cool, isn't it? Okay. So that's one thing, and then the second thing was, as you said, we can use a single number to represent a two-dimensional coordinate map. Okay? But what is even more cool is if we can fold 2D space into 1D, what about three-dimensional?
2D space.
You can pick any, exactly, so with a three-dimensional space, you can pick any two axes, fold it into one space, one dimensional first, and then whatever that dimension becomes, fold it one more time with the leftover dimension, and now you have a single dimensional space again.
So what about a fourth and a fifth?
It's the same thing. Give me a fixed number of dimensions, I can always fold all of those into just natural numbers. And it's not just that. If you give me any natural number, I can reverse it back to any coordinate if you just tell me how many dimensions it is supposed to map back into.
Okay, that's cool.
I think it's really cool. I just don't know a real application of that just yet.
You're trying to make a comic book, yeah.
Yep.
When the monitor, or I guess when the graphics card, like let's say, figures out what you color each pixel and stuff, is it more space efficient to store everything as in one dimension rather than two dimensions for each pixel?
I don't think it's any more efficient in general because you still have the same total number of things to represent. So when you think about the worst case, you still have the same number of zeros and ones. Okay, so that we cannot change. On the other hand, yep, go ahead.
I was thinking you can automatically have a program write itself its own arrays or something like that.
Unpack something into an array.
Yeah.
Because you can pack an entire array into a single number.
Yeah.
Oh, wow. That's some benefit.
So that's kind of cool, but you have to know ahead of time, the size of the array first, because that determines how, and also how you fold the space too. So however you fold the space, when you unfold it has to be in the reverse order, exact reverse order.
Okay.
Yep.
That'd be really cool.
Yep. But I think it is kind of cool that, because it's counterintuitive. Because if you ask someone and say, okay, what about, can you compare the cardinality of a 2D space to just one of the axes of the 2D space? Most people who understand, set theory and stuff like that would not even imagine that they have the same cardinality. But they do. I mean, remember, the first thing that we encountered was the number line. The number line of integers and the number line of natural numbers. So that's kind of baffling already that they actually have the same cardinality, because you would think that because natural numbers is a subset of integers, that they would not have the same cardinality, but they do. But now we're dealing with a two-dimensional space where each line, quote unquote, each line in a two-dimensional space is a subset of the natural number, or the natural number is a subset, or is the same as each line. So you would think that there's no way we can actually map a two-dimensional space to a single-dimensional space in a way that is bijective, but we do. So I personally think it's kind of profound that we can actually do stuff like that.
You just gotta find it in the application.
Well, I'll leave it to someone to find a real-life application. Yep.
Did you figure this out?
Yes. So I read about the way to count diagonally from other websites. So people show that yes, we can fold the space. So that part is not from me, but the equations are, especially the inverse function. Yep.
Where'd you get your doctorate in again?
Where?
No, what?
What? I don't think you can see it online, but let me try anyway. It's called stochastic admissible heuristic search. I don't think you can find it online.
Oh, I thought that was the degree.
What?
What are those words?
Okay, each word has a very specific meaning in computer science. Okay. Stochastic means it is non-deterministic. Okay. Non-deterministic means it is probabilistic.
Yeah.
Okay. Admissible is strange. Admissible, we'll actually get to that at the end of this semester. Admissible means whatever heuristic you're using, or a guess of the actual number, you're always underestimating. Heuristic is basically a rule of thumb, a very quick way to estimate something, but it's always underestimating because of the admissible part. Okay, give you a quick example. Okay, what is the distance, the actual distance, okay, on the road from here to, I don't know, the state capital? Okay, well, you kind of have to trace the route a little bit, or just ask Google. It will give you the actual miles that you have to travel to get to the state capital. But a very quick way is to draw a straight line and just measure that straight line. Okay, but that straight line is always going to be an underestimate, because the actual distance has to be longer than the diagonal line. Unless you have, wormhole technology, then you can go.
Well, that's not hard to. Oh, anyway, no. So my question was this. So everything that we learned about the pixel infantry, again, if I want to do some outside research, what
Outside research on what?
On what we just talked.
On what we just talked about?
Yeah. No, it's just that because I just forgot, because we did signal notation and then I forgot the name. That's what I'm trying to.
The sigma notation.
Like after we did signal notation and then we went into the graph, and I was just trying to see what was the name of in your notes. When we was doing the graph, what was the name of it? That's all I was trying to ask.
I don't know whether there is a name or not, but if you look up Aleph null, two-dimensional space, one-dimensional space, you might find it. Because I did some research on my own, and that's how I found the diagonal way of counting. Go like, oh, that's kind of cool.
It's just Aleph null dimensions.
Aleph null 2D to 1D or something like that.
Okay, that was it. Because that was it.
So, are there any questions about the pine needles? Oh, actually, I keep forgetting this, so I'm gonna pass this out now. The roll sheet, yes. I've been bringing the roll sheet every single day, and every single time I forget. Okay. So I'm just gonna. There are two sheets, just initial name, your name, next to it. Initial next to your name. Or I can just put it at the door. You guys can sign it before you get out. Either way. Are there any questions though? Are there any questions about the pine needles, the pine trees, or the pine forest? Yep.
I just because when I believe all the stuff we did, there's some ways like a very, very perfect scale of just wondering, the equation that you're using, are we gonna be using that same equation to solve every problem? Or
No.
or
But it will be in the exam.
oh, so we just
You will not be asked to derive the equation, but you may be asked to utilize the equation
okay, cool.
to solve certain problems.
Yeah, that was the question I was trying to ask earlier. I just not know how to ask it.
Yep.
To extend the theorem a little bit, is the 3D space has the same continuity as
Yes.
the 1D?
Yes. Because you can fold, you can pick any two axes of the 3D space, fold it first into one dimension. So now you have a two-dimensional space, but we already know a two-dimensional space can fold into one-dimensional space. So any dimension can fold into just natural numbers. That is the cool part of it. Yep.
So for a 3D space, can you just add a Z as well?
Yeah. So the idea of a 3D space, okay, that's a very good question. Okay, so let's say you're dealing with H, okay, so you're trying to find out, how to map X, Y, Z to a single number, okay? There are different ways to do it. So you can say H, X, Y, Z.
We're not seeing the
Oh, okay. I'm not showing the tablet. There we go. Okay. So you can use a G and then use another G, and you can just say, okay, I'm gonna map X, Y first to a single dimension, and then we'll combine that to Z to map to the other single dimension. So you have to apply G twice anyway, okay? But the order is entirely up to you. I mean, if you want it to be weird, okay? I don't know why you want to do it this way, but you can always say, I'm gonna fold X on its own, and then G of Z, Y. You can always do it like this too. Now the extra parentheses are actually necessary because x, y is that we don't have two parameters to the function. X, y is a single pixel, and that is the parameter to the function. So that's why the extra parentheses may look kind of go like, are we double parenthesizing this whole thing? No, we are not double. It's not duplicate. Okay, the extra parentheses actually serves a purpose. The inner parentheses is indicating it is a two-tuple, and then the outer parentheses has to do with the application of a function. Yep.
Could it be like 1 pixel in X, Y maps to 1 pixel in Z? I mean 1 point in Z. So then.
No. Whatever x, y maps to in this case is a dimension on its own, but it's the collapsed. It's the x, y dimension, which is a plane collapsed into a single dimension. So because that is also a dimension, you have to combine it with Z so that you fold everything into a single final dimension.
It's kind of hard to think of how the numbers would go because one of them is the diagonals. So that's
Yeah.
like these two.
Yeah, but we don't care because we already know what G is. We just need to know that G is a bijective function that can map a two-dimensional space to one. That's all we need to know. Because however that mapping is done, it's folding, a two-dimensional space, the xy plane of this 3D space into one dimension. And now we have another dimension Z that is left over, so we can combine these two by using another application of G. You can plug in numbers. I mean, you can just plug in, numbers like, in a particular order, so you can actually look at how the final value of H would come out as. Yep.
So I understand there's no such real thing as 4D, but you can actually, by this you can do 4D as well.
Yep. Mm-hmm. Yep. As I said, I have no idea why or how it can be actually applicable, but it's kind of cool.
Yeah.
Yep.
So what's the name of these equations that you're doing?
I don't have a name for that.
Oh, there you go.
You can call it tax equation.
Well, no, because I'm
Tax, space collapsing equation.
no, because what happened is I wanted to go home and practice these, what I'm saying, before I forget them. So that's.
How about this? Tax Thanos defeating space collapsing equation.
That is awesome, but too long right now.
I don't need no infinity stones because I can collapse space.
Hold on for a second. How many more time?
Large amounts.
Hmm?
There's no infinity, right? So you're just saying there are large amounts of stone and you'll just collapse it down. Infinity doesn't exist.
We don't have to deal with infinity, but we do have to compare cardinalities, right?
Yeah, the one.
Yep.
I'll have no stone.
Yep.
Types the most strongest in the DC and the Marvel universe.
The one stone that rules
The
them
one
all.
stone that rules
Yes.
Could you fold one dimension to zero dimension? Remove it like that.
Nope. Well, that would not be. That would definitely not be injective, right?
We got to
That would not be injective. You can have a function to map everything into zero as a single point, but it would not be injective anymore.
Yeah, you're like, I collect what else done.
Alrighty, I'll see you guys on Wednesday.
So just making sure you meant to put close parentheses right there, right? I swear.
Yeah, there's an opening right before the one.
Right, so that should be closed.
Yeah.
Okay. When your office hours again?
It's in the syllabus. Usually it is right before the class. This class. So on Wednesday it's going to be right before this class. But I have it over at the design hub.
Okay.
Yep. So not in my office,
I
but
want to
over at
see
the
you in the
design hub.
question quiz.
Yeah, that's fine. Yeah. Or you can just email.
Oh, yeah.